I'm John Hazel, your host for today, and we're going to talk about a number of different things. Really, how we designed our POD, what our results are, and the impact that it has on our testing. A couple of things that we're really trying to accomplish here is safe operation of tanks, and really trying to minimize the number of confined space man hours that are allotted for each and every tank inspection, but also providing the highest level of confidence in the data so that you can make the best decision in the operation of your tank. And obviously, if we can keep tanks in service longer, that asset provides more value to your organization. We've got a short video here just depicting on how, some of the things we run into in our slide launcher and how that looks in the execution of an inspection. So this is really designed for your low flash point so that we can control that atmosphere and launch into the tank for your gasolines and other items, other products. This is performing a navigation, or your INS, setting your navigation so that we can inspect your tank bottom. And this is our ultrasonic transducers on the very back end here. Our overall coverage, these are autonomous scanning patterns that we set up for each of our run tracks and able to cover a very high percentage of the tank bottom here and get very close to that shell to bottom weld within a quarter of an inch or so. And then, the exit of the tank. So a couple of things that we really wanted to set out and do is when we're talking about data quality, we need to make sure that the data that we're providing meets the industry standards. So does our data meet the Annex G guidelines in 653? And I know that's going into a different document, but we've also done a number of things across our timeline here. We've had blind testing. We've done back-to-back field comparisons where the tanks that we've inspected have been followed up with MFL inspections in a number of different times to compare results. We've also done a lot of lab work on the probability detection, looking at a number of different defects, and also making sure that we can prove that our sensors are calibrated and they're functioning correctly. From a data coverage standpoint, we've really identified the factors that impact us the most. Obviously the tank drawings, we need to know what's installed in your tank and what kind of impact those obstructions might be for us. That helps us to build our exclusion areas so that we can protect the robot and make sure that everything is operating correctly. But also some of the other things that we're going to ask about is what kind of sediment level and type are you expecting in this tank? Because that can impact the overall success of the inspection. And we're also going to look at product characteristics. And this is really going to be, is it a uniform product or is there a water layer there that can impact our ability to navigate inside the tank? And the other item that we're going to look at is the flow. And we're going to model that flow. We can operate in a tank that is flowing, but we just want to see how the currents that are established by flowing in and out of the tank impact the robot when we're operating. And as obviously, we are API 653 compliant and meets all the criteria established in API 653 for an in-service inspection. Want to cover a little bit about our testing system. We've landed on a 10 megahertz transducer, which provides us the best scenario from the standpoint of we can see through some sediment or the thinner stuff, but also provide the resolution. And we'll talk a little bit about what kind of near service resolution we can see with the phased array as we get deeper into the POD study. But also, so the other thing is that we're covering a 14 inch wide swath. So that's a pretty wide area. And in order to prove what we're doing here, we've constructed a calibration plate or a function test plate that meets the typical standard at 0 to to 500, so that we can prove that and measure across that entire expected thickness across on the tank bottom. And this would be the B scan for that, so you can see the 5-step wedge. Very clean presentation there. This is the overall iterations of where we started in the process. So we started with just the Annex G, and how do we stack up with what we're measuring to what the industry expects. So we had our first plate with this, and as you can see, our data was very close, even at that time. We've performed blind tests also from customers that provided plates for us to scan. We actually had a laser scan of that and compared our PAUT scan with that, so you can see a very high correlation and overlap between the data. This is our latest iteration of the test. So we have 176 total defects, but 124 of them are really part of the POD test, and 124 meet Annex G per API 653. So the criteria that we used for this, we really wanted to know, can the robot see it? You know, could we measure it once we did see it? And what is the estimated remaining thickness? And for coated areas, which we did have a couple of areas that were coated, and we'll go over the plate here in a minute, what's the remaining thickness of the discontinuity? And what is the coating thickness over that discontinuity? So that was our 4 objectives when we started. This is the current plate, and you can see we've got a number of different configurations. We actually have a couple of holes that you can see here, overlapping indications, and a cluster of indications, just to kind of get a flavor for how the ultrasonic impacts, or how is it going to be measured and displayed in our system. This is a combination of those two. We've got the fabrication drawing plus the C-scan representation coming out of our system. And as you can see, that everything is lined up, so our positioning system works very well. And the correlation for where something is there is an indication or discontinuity there. There are a couple of places where we do have a little bit of noise, but in each one of these areas, it would be followed up by looking at that. The analyst would look at that area specifically for confirmation. We also looked at the different collection speeds. As you can see that, these first two, there's not much of a difference there. This is the one that we selected, which is 6 inches per second, which meets the ASME standard or ASME code. As we go beyond that, we're 0.19 meters per second. We do start to see some distortion and some things just rolling off. From, performing a lot of manual testing in my career, 6 inches per second sounds like an easy thing. It's really not that fast. And on a single element, that would be true. But when you have 256 of them, we're happy to have this data recorded so it's repeatable and we can look at all the data in our own time. And this produces quite a bit of data, collecting about 188 readings per square foot. We also looked at the accuracy, and the accuracy over the range. We tried to display it in a number of different ways, but landed on this unity plot. So in a perfect world, everything would be right on the line. So this is vertical axis is what was measured physically with either a mic or some other means. Horizontal axis is what was measured with ultrasonics. So as we can see that most everything is a little bit above the line, which makes sense to me because ultrasonics is going to measure things a little bit thinner than they actually are. And when I say thinner, it's like 1 or 2 mils is what we're seeing here. It's the correlation from actual to measured is very tight for us. And as you can see along the normal axis here, and we'll get into this data a little bit later, everything falls within 3 standard deviations. So this first aspect here, this is product side and soil side displayed together. And what we get is a standard deviation of 0.0044. So that's, 4 mils for all 176 discontinuities here. 95% confidence level of 0.0012. So very tight range that we're operating in here. It's going to be the same for soil side and product side here. Confidence level 0.0013 and 0.0015. So extremely tight tolerances in what we're measuring. The other thing that I would point out here too is that it wasn't just one person that took this exam for us and provided all the data. We actually had 3 to 4 different people looking at all the defects to make sure we had consensus across the range of what we were inspecting. Just to make sure that we didn't have a fluke here or there. If something is true, it's always repeatable. And that's exactly what we're finding in this case. The other piece of information that we looked at is really what's the other impact for ultrasonic testing? You've got remaining thickness, which we just showed that we've got a very high correlation across the expected thickness ranges there. The next component for us is the diameter. As we can see, the smaller the diameter, the more variability we run into. At a 1/16 of an inch diameter, I think we only had one of them in there in the test, and we didn't see that. So even at an 1/8 of an inch diameter, we found some of them, but not all of them, and up to 3/16 of an inch. Beyond that, we were able to find and measure everything else in the plate. So this is the part of the Annex G. This is the indications that must be found less than 050, which we were able to find everything. We had to do 70 to 90% in, a half to an 050, and we were able to find 100%. And 2/3 to a half, and we had to find 40 to 60% of those, and we found 93%. Again, I think the main difference here is the diameter. So we know the smaller the diameter, the more difficult it's going to be for us, especially because we're dealing with hemispherically shaped discontinuities here that return just a very, very small amount of sound for us to detect and measure. Aside from those things, some of the other factors that we've taken on is the pitch and roll, because we know as we're traversing across the tank bottom, the robot is going to pitch and roll, which is going to impact the angle of incidence for the ultrasonic transducer to the plate bottom. So we tested in 3 different ways. We had 0 degree, and then we did 5 degrees pitch and roll. So side to side, and 5 degrees with the robot long. And I want to say also that the 5 degrees is important because that is double the amount of tilt that we would expect to see when we're going across a shell to bottom weld, or not a shell to bottom weld, but a lap plate weld in the tank. And at that degree of pitch and roll, again, everything was minimal, or the impacts that we saw were very minimal. 0.91 to a 0.96, 0.30 actual coating thickness to a 0.027. So essentially, we did not see any measurable differences with that amount of pitch and roll in the tank. So, and this is actually from our test tank here in Houston. This is our gantry that our engineers are using in Boston. So we've gone across everything in both scenarios and looked at the data. Again, the qualification piece was 128 defects. We do have 176 discontinuities in the plate, with a 0.00 remaining thickness being the lowest. And we were able to resolve this quite readily. And most of the time, what we're finding in in contact testing is normally around 0.040 was the limit of what the thickness that you'd be able to resolve. But in our scenario with the higher frequency transducer and the added standoff that we're applying here, we're able to measure down to that 0.022 and possibly a little bit thinner. We didn't quite get to the limits of the minimum resolvable thickness here. And we actually had three different plates. So talking about our pitch and roll again, the different speeds, the different, -5, 2 + 5, and the sediment and plates or sediment that we run into. And looking at the next plate here is our coating thickness. Now the coating thickness, what we've seen in normal epoxy coatings is really not much of an impact for us. Some of the more exotic coatings that we run into could pose some issues, but most of the coatings that we're seeing in tanks today are fairly uniform, thin film epoxy, and that certainly poses no issue for us. As the coatings become thicker, that does create new limitations for us and the accuracy of the testing that we're going to see. But we're still able to test through those coatings and make the measurements to provide you the data that you need to ascertain the condition of your tank. A couple of the different scenarios and what is the overall impact that we're going to see on a tank. Fine sediment and unconsolidated. With our B-scan here, you can see nice, steady lines, and that's multiples of the tank bottom thickness that you see there. Would be no issue for us. Rust, scale, or sediment, unconsolidated here. Again, a moderate impact on the PAUT and minor impact on the mobility. And as you can see, it's just the B-scan starts to become a little noisier, but still measurable and still usable data. Now, once we get into rust, scale, sediment, and consolidated, something that's a little bit more substantial, we get major defects or major impacts on our phased array and moderate impacts on how we can move across the tank bottom. And you can see in the B-scan here, this above, that is all the reflectors in the sediment. So it's really attenuating the sound here where we have points where we can get some measurements, but a lot of areas where there's just very little sound being returned. Mud, again, is going to be kind of the same thing where it attenuates the sound so much that we really don't get any usable data. Sludge and sediment, the same as mud. It's just not too much that we can do there. So for non-homogeneous product layers at the bottom, again, we do have, it's a moderate impact, but in most cases, we can get very usable data across the entire tank bottom. So getting into this, I do wanted to take a little bit of time to go over some of the specific indications that we'll run into and have a little comparison between what we see in the field conditions and what we saw on our POD. The first thing we have here is an O200 remaining. So we can see here nice strong signals. You can see where you start to see a little shadowing in the B-scan here, especially in the multiples. So this is 200 remaining in live conditions, and this is 200 remaining on our POD. This certainly is a cleaner signal, but certainly we have repetitive here and that's one of the things that we're going to look at to really prove the indications how repetitive it is across the range. This is an 050 remaining that we do see, and kind of look at the signal quality here. So easily measurable in both circumstances, and really you can pick out this in the B-scan here. This is going to be a much larger diameter than what we would see on our POD test. So it's just going to make it stand out that much more. And then one of the next things that I was always curious about is, what happens when you see a hole or when you find a hole? Do we ever find a hole? It's kind of one of those things that, being in tanks for 25 years, I've just always wondered about, and happened to be part of our test here. As you can see, we don't get any return on our A scan, or very small return based on geometry here. This indication is actually from the bottom of the container where it's measured the full sound path there. But what we'll see here is that because of the consistency of the UT data that we're seeing and the number of multiples that we have, we can traverse a little bit to the left, get to a good ultrasonic signal, and actually be able to see it walk into, just like you would if you were manually performing that in the field, and to the other side. So there is a detection means for us to detect and find holes on a tank bottom. So in conclusion, the detection and measurement capabilities that from the system are robust, and we continue to define the limits and capabilities and identify ways to improve. So we're very much on a continuous improvement track here. And we have actually started a second phase to the probability of detection study, and that's going to focus more on the diameters and what kind of impacts that has on the signals that we see, so we can start seeing, what our true limits are. And at this time, we'd like to open it up to any questions. And again, thank you for your time. Okay, first question we have here is Square Robot performing any other internal tests of the PAUT system? And for that, I would say yes. We start out the day with our function test, so that we are measuring across the 5-step wedge, so we can prove it that way. And then we're also, when we set up in the tank, we are seeing multiples that we'll be able to take those multiples off of the tank bottom and make sure that everything makes sense. So certainly we are looking at the overall condition of the data that we would see. Okay, and I've got John Richards that's going to come in and help me answer some of these questions as well. John has been a valuable member of the team and was very instrumental in performing a lot of the testing for the POD.
How are you guys doing
Welcome,
today?
John. Thank you for attending with us today.
Not a problem, not a problem. All right, how does the framework address signal variability due to material changes or corrosion profiles? Currently, the way we're set up, the signal variability, we are able to see with our PAUT system through, there was also a question of the non-homogeneous layer, and did we do a water draw to pull that out? I was in the middle of typing a larger answer for that, so let me just quickly, we can actually see through a lot of the non-homogeneous layer, or the rag layer that sits on the bottom of the tank. It can interfere with our signal, yes, but we're still able to get proper echoes through the bottom of it. But any kind of water draw that would pull that out would help. Now, how that creates it with the signal variability, material changes, generally, we don't see too much of a material change in the bottom. If there is rust or scale, that will attenuate our signal. And as the sound travels through that rust or scale and then tries to go through the steel, we will lose signal. So that goes into part of with the brush working and getting rid of all of that. The corrosion profiles, we're able to see really well soil side and product side corrosion. We're able to determine the walking of it. A lot of the product side corrosion depths we can measure, but with the reflection and refraction, we do sometimes lose our signal. So what we'll do is we'll give you the best quality signal that we can see and let you know that. John, if you want to fill in any blanks I left.
I think you covered everything quite well there. Thank you. Okay, has Square Robot inspected any crude tanks? And to date, we have not inspected any at this time. And I would say that the limitation that we run into realistically is the amount of sediment that we would expect to see in those tanks. Certainly, we're in clean products most of the time now, but even in some of those are red dye diesel, it's not a visual that we're using to navigate around the tank. So our system is certainly built for that. It's just with the amount of sediment that you have in a crude tank, it's not something that we've used or attempted at this time. If we did have the sediment, certainly I think it would be a possibility, and one of the things that we would look at. Did you generate accuracy 95% values for different types of sludge on the tank bottom? And I think, John, I'll let you take this because you were more involved in that than I was, but.
So for the actual POD testing that we did, we were not able to actually recreate any sludge. All of our data on that is just from our experiences in the tank. And generally, the more sludge that's in the tank, not only does it restrict the robot movement, but we're also unable to get PAUT through that different amount of sludge, especially if it's very thick. The signal will just attenuate and it won't be able to make its pathway down to the steel impact up to the transducer. So that is where we're at with sludge. We're working on different ways, constantly trying to get better. But unfortunately, thick sludge is a real stopping point for the robot currently right now.
And I would think at some point you're going to get to a point of diminishing returns where it's just, it doesn't matter what you find because you can't make any of the measurements anyway, just because of the physics of the problem that we're trying to solve. Okay, how is detection reliability quantified across variable tank bottom conditions? And I think this is an interesting question because, one of the things we say about tanks is they're all round, but none of them are the same. And we're going to see that across a tank bottom as well, where you have different slopes and you have different conditions, different configurations where you have higher levels of patch plates over here where you may not over here. But realistically, what we're looking at from a detection and reliability standpoint is how many multiples and what are the strength of the multiples that we're seeing across the sound path that we're measuring. As long as we are seeing good, strong multiples there, we have a high degree of confidence that we're going to be able to produce the right information for you. And how accurate is the positioning of across the tank bottom? So when we have a discontinuity there, how accurate can we be there? And what we're saying is typically we're within a 6-inch circle. Is about where we can be. I believe that's where we are. I will say that we've recently had the pleasure or the ability to go in and re-inspect a tank that we inspected and looked at the data on top of each other. And we're actually, the accuracy of that data was very good. So it was everything that we said was there before. It was there the second time, which you would expect it to be, but it was also from the positioning standpoint, it was in the same place.
Correct. It was found. We found it in the same areas of the same plates, and we actually, over the past 2 years, we noted that there was still some wall loss that we were actually able to see, like from point A to point B. So it was pretty accurate. It was real reassuring to see that on the back-to-back like that.
Yeah, and that's for a young service like this. You don't get the opportunity to do back-to-backs. Normally you're not going into the same tank that often. So that was a very, very good opportunity for us. If a recordable indication is found that needs repair, do you guys come back after the tank is cleaned and mark up the indications for the repair contractor? Certainly, that is a number of different ways that we can handle that. Certainly, we can provide the X and Y coordinates and go out and mark those up and prove them up. Just this is everything that needs to be done there. Or we can provide the coordinates to the repair contractor. It really depends on what the circumstance calls for.
In the report that we provide also, we do give an X and Y coordinate from where the plates are. Depending on where, we'll let you know if it's like the southwest corner or the northeast corner where you take their measurements for the X and Y. But yeah, currently we have not gone back into a tank and marked it up, but we do try to provide a map, as much detail. And you can always contact us again and ask more questions. And we work with every client one-on-one just to make sure they're getting what they want.
And the other side of that is most of the tanks that we go into are tanks that they're wanting to extend the life on. So we're not getting to that scenario where they're expecting to have to take the tank out of service to perform a repair. So it's more, we were really trying to extend that service, whether it's, another 4 or 5 or 10, 15 years, depending on the condition of the tank. Can you share a comprehensive POD report with customers, and how do they obtain that? How can you share?
I think if they have an NDA signed with us, they can contact any sales rep that we have, and we should be able to provide a deeper dive into the POD that we completed.
Right.
But I think that is how you would go about getting the actual comprehensive POD version of that.
And that there's a lot of data. There's data in it, and the guys that drafted the report did very well and looked at it from a number of different options and angles to really kind of make sure we understood what we thought we understood.
Yeah, Evan did a great job on that.
Yeah, it's drafted by engineer type, so it's very entertaining. Okay, what is the minimum size tank opening you need to deploy the robot? Right now, we're a 24-inch manway.
Correct.
Whether it's the side entry for the side launcher or for the roof. The roof one does not. We've been in through square one, so it doesn't have to be round. We launched through a square one, but still is the 24-inch opening is what we're looking for. Okay, so what is the percent of area typically covered with square robots? So this is going to be variable, and I will say that it depends on the configuration of the tank. How many columns are there? Are there mixers? Is there internal piping? From a standpoint of, what could we catch? What could we inspect in a wide open tank? We'd be able to get 95% of the tank bottom. As we start seeing other appurtenances and columns installed, it does get reduced a little bit. But it could be, depending if you have floating suction, if you have a Coflex opposed drain, we start then having to make decisions of what coverage is really going to produce results for you. Can we perform an EVA or a statistical analysis at 25% and give you an indication of this tank bottom? We're not seeing any corrosion, and we're not really seeing anything that dictates that the tank needs to come out of service and it can't be installed. So, as long as we can prove what that corrosion rate is, there are different levels of inspection that we can run into. And it might be that 95% coverage that we can produce, or we might be 50, 60, 70, 80. It just depends on what equipment is installed into the tank. Is it possible to make a robot to break up solids off the tank bottom in some cases? Certainly with enough resources, anything is possible. Is it necessarily the level of effort that's going to be required to do that? So it would be difficult to make one that suits all purposes. So if you have something that's tightly adhered, that's going to be a different robot than something like what we have where we're just trying to move sludge and debris around, where we just have a little brush. So there's a number of different things. It's possible, but once you get too specific in what you're trying to do, it limits its ability to be deployed in all circumstances.
Yeah, generally, currently our robots we have the brush on the front end. So if it's a solid and that brush isn't going to be able to move it, we're not going to be able to move it. So currently we don't have anything, I don't think, in the works that will break up solids off the bottom of a tank. But that doesn't mean that in the future we won't. We're constantly trying to reimagine how to do this, and moving forward, we're not just going to create a single robot and be happy with that, which is pretty awesome.
Yeah, our product development is always full. We're always looking at different things and trying to solve new problems. Okay. Okay, can you define the material which has probability of maximum finding of defects during the PAUT test? So from that standpoint, the material that we're testing is going to be carbon steel.
Yeah.
We're we're not going to see too many clads or too many different combinations of materials in most tanks. And if you're talking about what causes the corrosion itself, then that's going to be the same as everything else. We can't really determine what's causing the corrosion with the equipment that we have installed.
I didn't understand how you can see holes in the floor in the UT data if it doesn't produce a clear signal. Can you explain again?
Yeah. In this particular case, what we would really see is the absence of data is what really produces the confirmation that there's a potential hole there. So once we would find something like that, we'd go to that area and then we would scroll in our data off to the left and off to the right on either side of that particular indication to make sure that, one, we have good strong signals on either side of the hole. That would tell us that there is something else there. It's not likely that we're going to be able to see a return signal from the bottom side of that hole in real world scenarios. So it's really going to be, what is the quality of data overall, and how does that across that line scan, how does the data behave? So if it's really kind of patchy and everything else, we may not be able to say for extreme certain that there's a hole there. But if the data is really clean, we'd be able to pick it out.
Yeah, on the corrosion, we would definitely see the walking. If there was a hole that was created by corrosion, we would see the walking of the corrosion and be able to get measurements of that. And then, just as John said, there would be an absence of sound. There would be no return because there's nothing for the sound to kick back up on us for. So we would look for that emptiness. In our system, it's just it would be blue. You saw the B scans earlier. There would be no lines going across anymore. So that would be our first indicator.
Okay. Well, I think that's it. Thank you for attending, everyone. And if there's any information that we can provide further to this, please reach out to one of our sales guys. My email address is there, and we'll be happy to respond and answer any questions as quick as possible.
Absolutely.
Thank you.
Thank you very much.